Hello, students and parents. Welcome to Concept Clarity. And today's topic is going to be about kinematic equations. So far, we have done basic maths. We have done seen the concepts of motion in 1D, and now we are going to see derive the equations required for solving various kinematic related problem. That means motion in a straight line related problem. So let us get started. We'll clear this. We have studied in acceleration that average acceleration is equal to change in velocity divided by time period. And we also know that average velocity is equal to change in displacement divided by time. Now, when acceleration is constant, when acceleration is constant, we have seen that we can represent it in graph this way. This is acceleration time graph. Then the velocity time graph, how will it be plotted? It will be plotted as a linear line, slanting line. And finally, the displacement graph, this is displacement, we'll call it xt graph, will look, how will it look? How will it look? It will look like a curve. Okay. So these are the graphs. You know, you need to remember this basic when acceleration is constant. When acceleration is constant, velocity time graph, linear, and then displacement time graph will be a non-linear time graph. Okay. So further to this, I'll recap. Average acceleration is equal to change in velocity divided by time, and average V average is equal to change in displacement divided by time. So now when acceleration is constant, then we can say that acceleration acceleration into time is equal to delta V. Now delta V, if u is the initial velocity, u is initial velocity, and v is final, then we can write this formula as at is equal to v minus u. So we can rearrange this and write it as v minus u is equal to at. This is our first formula of kinematics. So now from this particular formula of v average, from v average, we can say that displacement will represent displacement. We'll say delta x will represent it as s. Okay, going forward, will represent change in position or change in displacement as s. Okay, so we can write this equation as s is equal to v average into time. Right? We can write v average into time. V average avg into time. What is v average? V average we can write s is equal to initial plus final divided by 2 will be the average velocity, and this multiplied by time. So now this itself can be broken down into three parts. The first part, we can write v is equal to, how we can write v is equal to, from here, okay, I mean basically from here, from this equation, v is equal to, if I bring u this side, it will become u plus at. I can also write u is equal to v minus at. And if I want a time form, I'll say t is equal to v minus u by a, right? Right? From here, I can write in different forms. I can say v is equal to at plus u. I can say u is equal to vt minus at. And I can say t is equal to v minus u divided by a. Hope so far so clear. So now I can write displacement. I can write displacement equal to, I can put v, value of v in this particular formula. That means this is my first formula and this is my second formula. And the first formula I got from average velocity from here. And the second formula I got from, first formula I got from average acceleration, and second formula I got from average velocity. Okay. So now I put all possible forms of one into 2. So the first form of 1, this particular form I put in this equation. So v will become u plus at. If you do that, you'll get displacement is equal to ut plus half at square. If you put u is equal to v minus at, then you'll get displacement is equal to vt minus half at square. Then if you put time in this equation, then what you'll get? You'll get displacement is equal to, you'll get u plus v divided by 2, and time I put here, I'll get v minus u divided by a. So this will give me u square, right? I'll say it should be v square, v will be positive and u will be negative, minus u square, and the other uv and uv will get cancelled, divided by 2a. This can also be written as v square minus u square is equal to 2as. This is the other representation of the kinematic equation. I hope so far so good. I hope so far so good. Should I write the equation once over all over again? Let me write the equation again. This is how you're deriving it. First, you found out what is average acceleration. Average acceleration is change in velocity by time. So I'm reiterating whatever I said earlier. Average acceleration is change in velocity by time. And average velocity is change in displacement by time. And I'm saying the change in displacement will represent it with S. And this is the common representation used in most of our textbook. So acceleration, when we say acceleration is constant, when we keep acceleration constant and we assume u is the initial velocity and v is the final velocity, then we can write that change in velocity is equal to at, because a is constant. That means change in velocity can be written as final minus initial, v minus u. So v minus u is equal to at after rearranging this particular equation. So now from here, from this equation, from average velocity equation, we will get displacement. Displacement is equal to v into average velocity into time. And average velocity, if you want average velocity, you can add final and initial, divide by 2, multiply by t. So now you put all possible ways of 1 into 2, which is the second formula for for displacement. So these are the various forms of point 1. Three forms of point 1. One with respect to final velocity, initial velocity, and then time. Then you will get all the equations for displacement. I hope it's understandable. So shall I summarize it? I'll clear the screen now and I'm going to summarize it now. Okay, let me clear it out. Summary. So the kinematic equations. We have seen the kinematic equations, right? We have already derived it earlier using by keeping acceleration constant. Remember that this kinematic equation hold good when acceleration is constant. Is constant. If acceleration is not constant, then this kinematic equation will not hold good. But in not all cases, we have to evaluate the cases. But in most of the cases, it will hold good only when acceleration is constant. So the equation, the first equation which we saw was v is equal to u plus at. The second equation which we saw was displacement. S is displacement. Okay, we can call it delta x also. We can call it delta x also. S is equal to ut plus half at square, and S is equal to vt minus half at square. V square is equal to u square plus 2as. V average is equal to u plus v divided by 2. These are valid when valid when acceleration in bold acceleration is constant. Very important point. Most of the students make this mistake. Okay? They use this formula even when acceleration is not constant. So these can be used when acceleration is constant. Now, if you see the peculiar behavior, if you see, if you observe it very carefully, the first equation, in the first equation, we have velocity, we have final velocity, we have initial velocity, we have acceleration, we have time. What is missing? Displacement, right? Displacement. Displacement is not given here. That means this equation is independent of displacement. So when displacement is not given, and if you want to find out any of these values, you can use this equation. Now here you have displacement, you have time, you have initial velocity, you have acceleration too, but you don't have final velocity, right? Final velocity is not existing here. Here you don't have initial velocity, and here you don't have time, right? So each of the equation is unique. This is independent of displacement, this is independent of final velocity, this is independent of initial velocity, and this is independent of time. However, remember that change in velocity is equal to average acceleration into time holds good for any acceleration. It may be a constant or it may be a not a constant, right? Similarly, delta x is equal to v average into time holds good at all cases, valid always. Similarly, the integration is also valid always. That means delta x is equal to integral of v dt is also valid always. Delta v is equal to integral of a dt is also valid always, irrespective of whether acceleration is constant or keeps changing. These equations always hold good. I hope is clear. So please like, share, and subscribe. Thank you. Bye.